Okay, so this talk is about the software library HEAT, which is the abbreviation for the Helmholtz Analytics Toolkit. So let me just start with the motivation of our work. So in very short. So the first idea is many researchers and research software engineers use NumPy or SciPy or scikit-learn for array computations, for data analysis, and for machine learning. Yeah, and I would really want to stress that these libraries are great. They are really great, and there's no doubt about this. But in some situations, there might be some problems. So, for example, if you take these images from DLR, they are from a high-speed camera video from some rocket combustion tests. And if you group them into a matrix, you flatten the images to just vectors and so on, you get a matrix with roughly 200 gigabyte. And if you now want to do data analysis, for example, a truncated SVD of this matrix, you will easily run into the problem that NumPy, SciPy, and scikit-learn are limited to so-called shared memory systems. So basically a single machine. You can't add another machine like in an HPC cluster. You basically can use one node of an HPC cluster or your workstation. And if you look at the memory consumption, so the purple marker is the size of the data set itself, and if you want to apply truncated SVD, you already need about 400 gigabyte of RAM. And so if you have just a standard compute node in the DLR cluster, that's already too much, so I had to perform this test on a special node with 1 terabyte of RAM. And if you want to apply NumPy to compute the full SVD, so not the truncated one, you can't even take the full matrix on this much memory node. You can only take 40% of the columns. Another problem is, so I think every institution buys these super expensive GPUs, and they are really cool, but these three libraries are just not intended for GPU usage, so you can't take any profit from the GPUs. So our ultimate goal, and of course that's rather a vision than the status quo, so it's just a goal, develop a drop-in alternative for these libraries that is capable of distributed memory, so multi-node environments. So here you can see if you do this in the software library HEAT, you can easily use 3 or more nodes, and then the memory consumption per node goes down proportionally. So if you just think about that, if you would start with a much larger data set, then you couldn't handle them on a single node, but now you could still handle them on a higher number of nodes. And also we want to be capable of using GPU acceleration, so you can see here the green marker is the reference, so scikit-learn on a single node, of course with multi-threading, which is standard in scikit-learn. And if you use HEAT, for example, you can achieve a speed up, which is not that cool for CPU, but if you use GPU, you can really achieve a good speed up. And here this memory distributed setting becomes particularly important because GPUs have a comparably small memory, and there's no option. So you always have a large memory node with 1 terabyte of RAM, but you don't have a large memory GPU with 1 terabyte of RAM. So in this GPU setting, you really need multi-node setting. But of course, very important, I guess, these libraries are so cool because they are very easy to use. You can just do something without being an expert, and we want at least to try to keep this design principle. So also make it possible to use that for HPC non-experts. So in short, the vision basically is make array computing and data analysis or machine learning, so machine learning in the sense of scikit-learn, not in the sense of deep learning, as simple on a modern supercomputer as it is on a workstation. So that's at least our vision. So let me briefly go through the design principles. So I will just go through them, what is our idea. So heat allows for memory distributed, that is in a cluster, multi-node parallelism, and it's not limited to embarrassingly parallel applications. So that means you have embarrassingly parallel is if, for example, if you do Monte Carlo simulation, then you can basically say each node does something, in the end you collect the results. If you do SVD of a large data set, then you can't just say, okay, each node does an SVD, and in the end you have many SVDs, so that does not really work. You have to come up with a bit more algorithms that really require communication. It supports hardware acceleration, and here the idea is that this should be at least both NVIDIA and AMD. And very important, we want to have a simple NumPy and scikit-learn-like API that allows you to adapt existing codes and workflows rather easily. Hopefully with minimal changes only, and it should be accessible to HPC non-experts. So we don't want to have something like a scheduler that is called in your Python program. The next thing is we want to be vendor and platform independent and interoperable. So when I say platform independent, that's of course a bit difficult because we rely on PyTorch and MPI. We'll say some words about that later on. But I think having MPI on a cluster can be considered as being quite platform independent, at least until now. So maybe in 10 years this will be something very special. But so I'm sure your cluster will somehow support MPI. And also PyTorch is quite a standard thing, and in particular it's vendor independent in the sense that it allows to use many different kinds of devices. It does not work. Okay. So, and finally it's general purpose. So we try to do this array computing and machine learning stuff, but we don't have a concrete area of application in mind. And finally, unlike many other libraries that are similar in the scope, we are all scientists, and we also develop this having scientists in mind as users. So behind the scenes very briefly. So we do that in object-oriented Python, and the basic data structure is an n-dimensional array as in NumPy, but it's distributed. And distributed basically means if you take such an array, you can distribute it along parallel processes, and the idea is to split it along one axis. So you can split along the axis 0, along the axis 1, along the axis 2, and along further axes if you have more than 3 axes. So these local chunks of data are in PyTorch, so we can take advantage of everything that is available in PyTorch. So very good linear algebra on each process, in particular this vendor-independent GPU support of PyTorch, which is, I think, quite a good, cool feature of PyTorch. And what we do in Heat is we glue these local PyTorch objects together using MPI, and here we make use of this MPI for Py library, which is a wrapper for MPI, so that's this message passing interface for Python. And finally, the high-level routines like clustering, linear algebra, regression, and so on, they are designed with a NumPy or scikit-learn-like API, and we try to hide parallelization as much as possible. So the user should not require to take care for parallelization, him or herself. So now, since this is a conference about software engineering, I would like just to address some challenges in the development. So let me start with an overview over the team. So HEAT is a cooperation of DLR, Forschungszentrum Jülich, and KIT. And the head of the development team is Claudia, who is also in the audience. And of course, we also have student workers, and we have some external open source contributors on GitHub, mainly due to the Google Summer of Code 2 years ago. So working in the small but diverse core team is cool. So we have many different backgrounds. But of course, such a small team also can bring problems with it. So sometimes this onboarding, if somebody new joins, is really an overhead. So that's not trivial. And also, if somebody leaves, it's very easy that information gets lost. And also, even if you have perfectly commented code, if the person who understood the algorithm leaves and you have 1,000 lines of code left, even if it's commented, it's really difficult. So just as an outlook, it might be a cool idea to try this with modern techniques. So we already use the GitHub Copilot, but maybe also chatbots could be an option for the future. So regarding the quality, I just want. I think it's something with the CPU of the laptop is very slow because I have many objects on this slide. And, Does it not?
It's still not loading.
So I can just tell you, so you can already see the batches, so we try. So actually, I think all 3 institutions are somehow institutions that want to produce good quality software. So it's
not going to load, I'm sorry. I don't know what the problem is.
So
it shows as it's loaded, but it's not showing up here.
Okay, so I can just tell you, so we have different measures of ensuring quality. We use the Helmholtz code-based infrastructure for doing tests both on AMD and NVIDIA hardware. That sounds cool. The only problem is it's a single GPU only. It would, of course, be really cool to test that on a real HPC system. It's not only sporadically, but really to have the CI running on a HPC system. But I guess, you all know that's not that trivial. And we also do this continuous benchmarking, so where you just measure times of certain routines after each commit, and hopefully it looks like that. So you only see a drop in the runtime and no sudden increase, but also that would profit from moving that to dedicated HPC runners. So maybe we can go to the next slide. I skipped some points. We have quite many checks in there, and so I still can't go to the next slide. So, and of course it's always, and now it even destroyed some of the.
Unfortunately, it's not PowerPoint.
Okay. So
You should click it more. I think it's
so basically it's like always, I guess, in research software engineering, problems with you get funding for new features, but maybe not for maintenance, or usually not for maintenance. So, and we particularly want to extend the user group. So it's a really small project, and we want to gain more users, in particular outside of our host institutions. And so we are trying that with maybe an ESA project in the future. And so also an interesting question. So to which area does this belong? So because it's not mathematically enough to be regarded as algorithm research, So you can't publish that in the SCIAM journal on scientific computing. Yeah? But on the other hand, it's too much methods to be regarded as a direct application. Yeah, and with this, I'm already at the end of the presentation. So I have to press further, so feel free.
Uses any minutes of the elements, so they could click it repeatedly to show everything.
Yeah, I know. So feel free to try out if you want. Some of you already tried. So you can also suggest something. And here's also the code to GitHub. And finally, if you have questions, of course, and if you want to see the comparison slides to deRSE, you can also ask me. I can show you them later, but there's no time. Yeah, thank you very much for your attention.